Okay, so yesterday, well, on the first lesson, we talked about just sample spaces and how it can be time or volume or anything. And then we talked a little bit about using Pascal's triangle to count binomial probabilities. So in this lesson here, you're doing a die, and you're just trying to combine events into one event, that sort of thing. So this is like compound probability, I guess you could say. So here's the question. What is the probability of rolling a die and getting an odd number, or rolling a die and getting a 1 or 2? Okay? Or maybe the question will ask, what's the probability of rolling an odd number or rolling a 1 or 2? It's that kind of question you've seen before. This is where you start multiplying probabilities and that kind of thing. I teach it a little bit differently. I teach it totally from a set theory, like a set perspective, like a 12-1 style. So let me show you what I mean. Here, it's a single fair die, and it's rolled one time. Okay? So the sample space is just 1, 2, 3, 4, 5, 6. These are what could be face up on the dice. Event E is a subset of that. Actually, it's a proper subset because it's an odd number. So what are the odd numbers on a die? Just 1, 3, 5, right? The next one is event F. Event F is a 1 or 2. 1 or 2. So that's pretty explicit. 1 or 2. More importantly than writing out the sample space and the two event spaces is to measure them. What good does it do for us to draw a picture like this if we don't measure anything? Right? So we need to measure these spaces. So the measure of this sample space is clearly 6. The measure of this event space, E, is clearly 3. And the measure of this last space, F, is clearly 2, you see. I'm counting how many things I see in each set. So you're going to be using these for your numerators and denominators, you see. Okay, so I can actually already answer part C. Part C is saying, what's the probability that event E happens? So you could just say, well, that's just the number of elements in set E divided by the number of elements in set S. In other words, 3 out of 6. Notice I'm not even thinking about dice right now. I'm just using the symbols that I learned. The number of elements in set E divided by the number of elements in set S is the probability that E happens. So I forgot all about dice. I'm just using this formula. And it's 3 over 6. Practically, it makes perfect sense. That's a half. What is the probability of rolling an odd number when you roll a dice? Naturally, a half. Right? There are 3 odds and 3 evens. It's a 50-50 chance. Okay, but we're not trying to think. We're trying to use formulas right now. And we can confirm that it makes sense after the fact. What's the probability of F? Well, it's defined as number of elements in the F event space divided by the number of elements in the S sample space, which has got to be something over 6. So how many elements were in set F? 2, we said, right? 2. So this is 1/3. Yeah, of course, if you roll a die, the chances of getting a 1 or a 2 is a third. So 2 out of the 6 options available, right? Okay. What about this combo stuff, like E intersect F? Let's go back to part A. Do you remember from your set section, section 12.1, how do you form an intersection set using sets E and F? What does it mean to find the intersection set?
What they have in common.
Find what they have in common, right? So how many, or what do they have in common here? 1 is 1, 3, 5, 1 is 1, 2. What do they have in common?
1.
Uno, right. So 1 is the only number in common, and how many elements are in the set E intersect F? I just wrote a set for you. How many things are in it? 1, right. Let's look at the union set E and F. What numbers do you get if you combine sets E and F into one long set? A 1, a 2, a 3, and a 5. So how many elements are in the set E union F? 4, right. So now if I want to answer the question, what is the probability that E and F occurs, I can just look at the number of elements in E intersect F over the number of elements in the sample space. You said there was 1. The answer is 1/6. Now somebody else might say, hold on, this is so ridiculous. All I'm trying to do is enforce that we roll an odd number and that it's a 1 or a 2. Well, naturally, between 1 and 2 there's only one odd number, and that's just one of the 6 options. Yeah, you can do it that way. You can take the probability that event E happened, that's a half, times the probability that event F happened, that's a third, multiply them together, and that gives you 1/6. And that's a perfectly valid way to do it, and it's what you learned in the past. I'm trying to convince you there's a totally different way of thinking about it. The number of elements in the intersection set, 1, this one, divided by the number of elements in the event set represents also probability of A and B. I'm not multiplying probabilities, I'm combining sets first, see, and counting. Okay, so it's just this little different strategy. I'll just put a little note here, also can take probability of E times probability of F. You see? Same thing. Okay, let's go down to EUF. Well, you just measure the set EUF. What was in the set EUF? 4 things, right? So EUF had 4 things in it. We used the sample space, the same sample space the whole time. So 4/6. How could you have gotten 4/6 using the 1/2 and the 1/3? What's another way? You could also have done what? See, now it's not so obvious, maybe? Can you just use 1/2 plus 1/3? Does that work? Isn't that 5/6? Aren't you supposed to subtract the intersection? Okay, so you also could have used P of E plus P of F minus the intersection probability. That would work too, but I'm not sure it's faster. I know some of you are referring to this kind of stuff because it's what you learned 5, 6 years ago. Multiply the probabilities when it says and. Add the probabilities when it says or. Well, this means or. Be careful. You add 2 probabilities, always subtract the and case. Okay? So my method here is a little different. I'm teaching you to count your intersection set and your union set first and form a fraction, rather than thinking, oh, when do I multiply, when do I add? Forget that. Counting. It's all about counting. Okay? Once you've mastered counting, you can go back to the multiplying of things and adding of things together. Okay, and then I think we're down to our last few examples here. Here's the formula that I just basically wrote. You might recognize this from the other day. The other day I had something just like it, but it didn't have P's, it had N's, and I think it was A and B rather than E and F. But you know, that doesn't matter. What happens if I take this formula and I just divide by N of S? N of S, N of S, N of S. This is our 12.1 formula from 4 or 5 days ago. I just divide everything by the number of elements in sample space. What's the number of elements in the union space divided by number of elements in sample space? Probability of union, also known as OR probability. What's the number of elements in the event space divided by number of elements in sample space? That's the probability that E happens, you see, and so on. So I just turned this into a probability formula. We can even draw Venn diagrams for probability if we wanted to. Instead of universal set, we call it sample space now. It's the same thing. Okay, so let's try and use this guy in green here as sort of a formula. You did this in 12.1 too, it's almost the same thing. Okay, so I am looking for E intersects F's probability. So in this formula it goes like this. P E union F equals P of E plus P of F minus probability of intersection. And I'm being asked for this last thing, and I'm being told everything else. So this has actually been given, it's 0.4. and this is being given it's 0.2, and this is being given it's 0.3, and this is being asked for, so that's kind of like my x, you see. So what is x? You have 0.4 equals 0.5, take away what? X is 0.1, right? Okay, so I'll write my work on the top because I need more space. It was a bunch of given stuff and one unknown and pretty much a formula. Right? Let's look at part B. I switched things to R's and Q's, but that shouldn't bother you too much. You just change your formula to R's and Q's. So probability of R or Q is probability of R plus probability of Q minus probability of R and Q. I think they told us probability of R union Q. This was 0.6. It's given in the problem. They didn't tell us either of these, but they said they were the same. See? And then they asked us for them. So those are your x's. And they gave us this as 0.24. So literally just think of it as an equation. It's 0.6 equals 2x minus 0.24. So these are not hard at all. The most annoying thing is writing the question. Just so many symbols. So we get 2x equals 0.84, x equals 0.42. Okay? So you're just solving. Those are pretty easy because it's the formula. If you don't know the formula, it's kind of hard. And you should also know one last thing about this formula. This is also the same as when you read it out loud, okay? It sounds like this. The probability that the probability that either E happens or F happens is equal to the probability that E happens plus the probability that F happens minus the probability they both happen. That's literally what it means. Or you can think of it as soap bubble equals circle plus circle minus football. So I know that's silly, but soap bubble equals circle plus circle minus football. Remember in the Venn diagrams, a soap bubble is always a combination of two circles minus the part that's overlapping. So you see that visually. If you combine these two circles together in overlapping fashion, subtract out the football, then you will get this soap bubble region. So that's a great way to think of it when you're doing the Venn version of these problems. Sometimes they just hand you a Venn diagram. You could just think, oh, soap bubble is always circle plus circle minus football. Okay? Or snowman. Some people call that snowman when we first did it. Okay, now in real life, there are some things where the football never exists. Okay, in other words, it's impossible for both events to happen. So sometimes that formula up above will simplify to this. It's very possible that certain things you're talking about can't both happen. For example, rain, right? If the weather reporter states that the probability of rain is 0.4, you could probably assume that the probability of rain plus the probability of not rain is just naturally 1. I mean, it either rains on a day or it doesn't rain on a day, right? Even if it rains a little on a day, it rained on that day, right? So here you can see that the probability that it is raining or not raining is really just the probability that it is raining plus the probability it is not raining. There is no third possibility. There's no intersection. If you wanted to write the probability of rain and not rain, this term is 0, you see. This term is 0 because nature doesn't allow it. You can't have rain and not rain. It either rained or it didn't rain on that day. You cannot say it rained today and it didn't. That doesn't make any sense. Yeah, that's like my daughter saying, well, actually, that was more like my son saying, you know, well, I saw the mission, I didn't. That's kind of like saying it rained or didn't rain. Well, of course it rained or didn't. Now, if my son had said to my father, if he had said to my father, we solved it and we didn't solve it, then my father would have corrected him. Right? Do you remember what my son said to my father? He used or in his sentence. He didn't say anything wrong, he wasted his breath, right? He said, we solved it or we didn't. Yeah, thanks for wasting the oxygen in the room. But if he had said, we solved it and we didn't, I think my father-in-law would interject and say, hold on. You can't do both, right? You can't have it both ways. You either did or you didn't. You can't say you did both. No way. You see what I'm saying? Okay, so even in this mystery case, there's no and there. It either solved or wasn't solved. You can say it was solved or wasn't solved, but you can't say it was solved and it wasn't solved. No. Well, then it's not solved. Yeah. So what I'm saying is sometimes this term vanishes, and maybe quite often in real life, like rain. You either had a boy or a girl. You didn't. There's no third option. There's no boy-girl. Okay. Okay. So for this problem, what I'm saying is, if there was a 0.4 chance of rain, or 40% chance of rain, there was a 60% chance of no rain. There's like no third category. Okay, so the question is really simple. There's no need to think this much. We're just trying to convince you that the football there is 0. There is no third term there on the right. Let's look at the London, Seattle, Taipei example. Now I wish, when I had first learned this, that somebody would have taught me this method. But if you make a table where this is London, Seattle, Taipei, and this column is rain, no rain. And if you take the time, the 30 seconds, to fill this table in, it makes these problems so easy. Okay, let's look at this. The probabilities of rain in London, Seattle, and Taipei are 0.8, 0.6, and 0.7 respectively. That means that the probabilities of no rain are just naturally 0.2, 0.4, and 0.3 respectively. So if you want to find the probability that it will rain in all 3 cities, probably the easiest way to do this is to just think of it this way. It's probability of rain in London times probability of rain in Seattle times probability of rain in Taipei. Just multiply the 3 red numbers. It's that simple. So let's do that on the calculator. 0.87. 0.8, times 0.7 times 0.6. 0.336. So I'll write my work here so you can see what I did. The next one says probability that it will rain in 2 of the 3 cities. Well, they didn't really tell us which cities. So it could be London and Seattle, not Taipei, you see. Or it could be London and Taipei, not Seattle, see. Or it could be not London and it's Seattle and Taipei that's raining, you see. So each of these would be found by multiplication. So you would just basically do this. London, 0.8, Seattle, 0.6, not raining in Taipei, use the 0.3. Plus, rain in London, 0.8, not in Seattle, use the 0.4. Yes, raining in Taipei, use the 0.7. Plus, not in London, use the 0.2. Yes in Seattle, 0.6. Yes in Taipei, 0.7. 0.8 times 0.6 times 0.3. Or, here's another victory case, so we're adding it. 0.4 times 0.8 times 0.7, or 0.2 times 0.6 times 0.7, 0.452. So the answer is 0.452. If you were in my Algebra 2 class last year, I taught it this way, and hopefully your other teacher did too, because it really is a nice, tidy way to organize your thoughts. And I can ask all sorts of nifty questions about cities reigning. Even if there's 10 cities, it really wouldn't be that hard to do. Okay, and then for our last two examples, what is the probability that in a group of 10 people, at least 2 have the same birthday? Do you think it's very likely that if I sat 10 people down, 2 of them would have the same birthday? I think that would be extremely rare. 2 people have the same birthday in a group of 10? That's pretty unusual. What about 3 people having the same birthday? Oh, that's slim. I don't think so. 4 people have the same birthday? 10 people, 4 have the same birthday. You think that's likely? No. No. 5?
No.
6?
No.
7?
No.
8?
No.
9?
No.
All 10?
Absolutely not.
Possible, not probable on any of those. Listen. How about 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9 or 10? What does or mean? Add. So while each of those cases was unlikely, adding them together might produce a pretty substantial probability. The answer to this question is surprisingly large. It's around 12%. Let's see why. First of all, this question is way too hard to answer. There's 10 people. We're trying to see the probability of at least 2 people having the same birthday. This question is just too hard for us to answer. Let's switch it to the complement event. What is the exact opposite of me saying at least 2 people have the same birthday? At least 2 people have same birthday. N is greater than or equal to 2, right? At least 2. What's the exact opposite of that? What's the exact opposite of n is greater than or equal to 2?
And is less than or equal to 1.
N is less than 2 is the complement. The exact opposite of n is greater than or equal to 2 is n is less than 2, technically. If I said I have $2 or more in my wallet, the exact opposite of that is I have less than $2 in my wallet. What does it mean for in a group of 10, less than 2 people have the same birthday? What's less than 2 people? 1 person. 1 person has the same birthday. That means what? It means everybody has their own birthday. So the opposite of this event is simply nobody has the same birthday. All have different birthdays. So I'll let you wrestle with that idea later. But the exact opposite of the sentence, at least 2 of you have the same birthday. The exact opposite of that sentence is everyone has a different birthday. And that probability is very easy to find. So my goal is to find probability of E by doing 1 minus the probability of its complement. Okay, so how do I find the probability of E's complement? Well, I need to ensure that everybody has a different birthday. Okay, so let's say I passed around a calendar. It's a blank calendar. And it's one of those year views, you know. You can see all 365 days on here. Just tiny little boxes. And I told the 10 people, hey, put an X on your birthday. Okay, just put an X on your birthday and then pass the paper. So the first person gets the paper. How many spots on there are available for them to X out? There are 365 spots there, right? What's the probability that they're going to X out a unique day that no one else has ever X'd out? Perfect probability, right? There's no X's on the date. They have a perfect chance of just marking any one of those, and they're not going to be duplicating someone else's birthday. The probability of the first person having a unique birthday is 365 out of 365. The calendar is passed to the person behind them. There's a red X chilling on the paper. Doesn't have to be the first spot. The second person gets it, looks at the paper. They're supposed to X out their birthday. What's the probability that they will not X the same spot? 364 and 365. Watch close. This all goes down to the 10th person, who is 356 over 365. The 10th person is actually 356. And the top here is simply 365 P10. The bottom is simply 365 to the 10th. And the answer is around 12% likely. Okay, so this last problem is it's really about a package. You can draw like a box if you want. Let's do that. Let's draw a little box like this. And then in the box are a bunch of cell phones. And 5 of them are actually broken. There's 20 phones altogether, but 5 of them are defective. But you can't tell because they're just defective, on the inside, something's wrong with them. So what I'm going to do is I'm going to draw 5 bad phones and 15 good ones. I'll just use B for bad, G for good. Okay? So you have 5 bad ones in here, and they're mixed in with a bunch of good ones. 15 of them. Okay, maybe I'll make the bad ones red. So, in this case, red is for bad. Okay? And you're going to reach into the box and just pull one out. You can't tell one from another, so you don't even have to be blindfolded. You're just going to pull out a phone. Then you pull out another phone, pull out a third phone. It says right here, 3 phones are selected. 3 phones are selected. Okay? Okay, because of the fact that you're picking 3 phones out of 20 phones, you already know your denominator is 20 phones, choose 3 phones. Okay? There are exactly 23 ways to pull 3 objects out of 20 objects. So, there's no doubt that's our denominator. The numerator just differs from experiment to experiment. So on our first case, we want all 3 to be defective. We want all 3 to be broken. So that's our first experiment. And so to do that, we're going to need to, from the 5 bad phones, we need to choose 3 bad phones. And from the 15 good phones, we need to choose no good phones. You see. So why did I put a times in the middle? It's because of the word and. When I reach into the box, I wish to pull out 3 bad phones from the 5 bad phones, and I wish to pull out 0 good phones from the 15 good phones. I want to do both. I want to accomplish both of these tasks. To get 3 of the 5 bad phones and to get 0 of the 15 good phones. Okay, this is the answer. So we're reaching into the box, we're pulling out 3 of the 5 bad phones, and none of the good phones, and altogether there are 20 phones. We're choosing 3. The calculator will give you the answer. So let's do that on the screen. So, just turn this on. We're going to type, basically, from the 5 bad phones, we are going to choose 3 bad phones, and from the 15 good phones, we're going to choose none, and then we're going to divide by, from the 20 phones, we're going to choose 3 phones, 3 generic phones of some kind. 0.00877, or if you press math, fraction, it's 1 out of 114. 1 out of 114. So I always like the fraction better. I just feel like my answers are more accurate, you know. I hate rounding. I always feel like I'm throwing away something important. Okay. Let's look at part B. Notice we're still pulling 3 phones from 20. So the bottom is still 20 phones. Choose 3 phones. But this time the desire is different. This time the desire is to get 2 bad phones. 1 good phone. So it's almost exactly the same. Actually, you're going to be doing this. From the 5 bad phones, I will choose 2 bad phones. And from the 15 good phones, I will choose 1 good phone. And if you type this, you'll see that it's actually 15 out of 114. Just type it the same way I typed a minute ago. Okay, now it's really important that you see this second problem as a 2-experiment compound probability situation. What's going on is we're trying to succeed at 2 things. 1, we're trying to get 2 bad phones. 2, we're trying to get 1 good phone. Okay? The nice thing about using the NCRs is it takes care of all the order in which this could have happened chronologically. So the NCRs are sort of non-order specific. So it includes all the cases where you got the bad phones first, and then you got the good one, or you got the good one first, and then the bad ones. You got the good one, then you got a bad one, you got a good one, you got a bad one. It's got all that order built into it, see? Because these are collection formulas. So they include all that. So it's awesome. So easy to do. 5 bad, 2 good, and I wish to have, 5 bad, take 2 bad, and I wish to have 15 good, take 1. See? Very nice. It's all very tidy. And the answer to part C is actually pretty simple too. So you get to part C. If you read it really carefully, it says, what's the probability that at least 2 are defective? You might want to change that into something that means, something a little simpler for yourself. For example, at least 2 means 2 or more, right? So how about just change it to this? What is the probability that exactly 2 are defective, or all 3 are defective? So I'm just kind of rewording it so I understand it better. Exactly 2 are defective, or all 3 are defective. Didn't we just do both of those calculations? Exactly 2 are defective is the answer to part B. All 3 are defective is the answer to part A. So now we're in a situation where we just don't care which case it is. We don't care if it's all 3 or just 2 of them, So since we're going to not care so much, our probability goes up. Our chances of success now are higher because we don't care which of these cases we get. Both are considered successes. So we add these together, and we get 16 out of 114. So obviously that's didn't do any work. But let me go ahead and write it for you as a combinatorial so you can see it. From the 5 bad phones, we will choose 2 bad phones. And from the 15 good phones, we will choose 1 good phone. Or, here's your plus. From the 5 bad phones, we will choose all 3 bad phones. And from the 15 good phones, we will choose none. No goods, please. All divided by, there are 20 phones, and I'm choosing 3 phones. So I love writing little subscripts. I just feel like when I do that, what I wrote and what I'm thinking are exactly the same thing. You know what I mean? I'm actually thinking about this experiment, getting 2 good phones, 2 bad phones or 3 bad phones. And this whole thing just reads the same thing I'm thinking. oh yeah, I get 2 bads and a good, or I would get 3 bads and no goods. I love that, how it just matches, the math grammar matches my English grammar, you know? It's perfect. So that's a nice thing. And you can see that this is really just, this first fraction, 5c2, 15c1 over 20c3, that's just our 1 out of 114. Actually, that's our 15 out of 114. And then the second fraction's right here, that's your 1 out of 14. But you can certainly type all this too if you want. Just type it all. Okay, so the combinatorials are nice because this problem could also have been done like this. This would be like old school method, you know? You go like this, you say, hey, I want to pick out listed part A real quick a different way. I won't do all 3 parts a different way, but I'll just show you one old school way to do part A. Maybe you remember doing this. Oh, there are 20 phones and 5 are good. No, there's 19 phones. I'm sorry, there's 20 phones and 5 are bad. Now there's 19 phones and 4 are bad. Oh, now there's 18 phones and 3 are bad. 60 over whatever 20 times 19 times 18 is. So let me get my calculator for that. Where'd it go? Oh, here it is. 20 times 19 times 18.
6 levels of 8.
Is it 6840? Yeah, that sounds right. See, this reduces to the 15, no, the 1 out of 114 that I had earlier. You see, there's nothing wrong with this method. It's actually a great method. The problem is, on certain problems, it can be too hard to think about stuff like this. Okay? But you see that 5, 4, 3, 20, 19, 18, those are like partial combinatorials. That's what the NCRs are doing for you. NCRs are handling all those little partial factorials and things. So it's kind of nice to use NCRs. That makes sense. Okay? All right. So let's go ahead and have you work on homework. Let me stop that.